Aloha, and welcome to this session of Shadow the Scientist, exploring the universe with the Gemini North telescope. My name is Jamika Marshall, and I'm very pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. The International Gemini Observatory consists of twin 8.1-meter optical infrared telescopes located on mountains in Hawaii on Maunakea and Chile on Cerro Pochon, which enables the telescopes to collectively access the entire night sky. Gemini Observatory utilizes the Q observing mode, in which science staff take observations on behalf of science teams from all over the world. In this session, we have the privilege of shadowing two members of the Gemini North observing team, Charlie and Jenny. They will be using the Gemini North telescope located near the summit of Mauna Kea, here on the island of Hawaii, with observations taking place remotely from the control room in the Hilo Base Facility. Control room, it's right behind me. Our guide on this cosmic journey will be Brian Lameau. And we also will have a special guest speaker for this session, Leilani Lozzi, which is the Hawaii Education and Engagement Manager here at Gemini North. Leilani, would you like to start us off?
Sure, happy to.
Thank you.
Aloha nui kako. Hi, everyone. Mahalo nui for joining Shadow the Scientist and the monthly public session. We're really happy to see you all here. It looks like Brian's jumping on the audio. I am here to just talk to you a little bit about our Hawaii education engagement programs that we're doing, mostly to offer up some advertising on some upcoming events in case you're based on Hawaii Island. But before I do that, I did want to honor the holiday today of La Kamehameha. It's Kamehameha Day, so some of you might have had the day off. I was very lucky to have the day off. This is very nice. But given that this is an online world and we have people joining from all over the world, we just wanted to honor this holiday and talk a little bit about what it's about. Who is Kamehameha? What is this holiday that we're celebrating in Hawaii? So I'm going to share this beautiful photo really quick. Hopefully you can see that. This is a statue of King Kamehameha, who is essentially the uniter of our Hawaiian Islands. So if you've never been to Hawaii at all, you've never seen it on a map, we are 8 different islands that comprise a state, the 50th state within the United States. And on our 8 different islands, we have various different amounts of people. One of the islands has the capital, all that sort of stuff. And before King Kamehameha, who united all of the islands successfully by 1810, we operated as sort of like chiefdoms or different, we had a lot of different elites or chiefs. And so every island had their own chiefs. Sometimes they had chiefs on different parts of the islands. The island that the Gemini Observatory is on is Hawaii Island, also known as the Big Island. So it is so big that you might have different chiefs on the different sides of the islands because there's so much space between the two of you. But essentially, King Kamehameha was the first to unite all of the islands. So he became the first ruler for all of the islands, and he created the Hawaiian Kingdom. And so every ruler after that, until the illegal overthrow of the Hawaiian Kingdom, was all a result of his efforts, of him uniting everyone. So King Kamehameha was born on Hawaii Island in the Kohala area. And so this particular statue is in Kohala. And on King Kamehameha Day, which is today, June 11th, there's different lei draping ceremonies and parades and other festivities that happen throughout the islands. Sometimes they're on the weekends, sometimes they're on the days of. And so I believe today at the statue was when the lei draping ceremony was had and different ceremonies to honor the king. There's a lot of great stories, of course, about how amazing he is and the things that he accomplished in his life. But there's also a pretty cool star-related story or sky-related story that's connected to his birth. So the exact date of King Kamehameha's birth is a bit of a mystery because, of course, there were prophecies foretelling the coming of a great king before he was born. And so I think some of the mystery comes from the fact that when he was born, it had to be kept a secret because there were chiefs of the island who were ready to kill any unique baby that was being born to other like high-powered individuals on the island at that time. So one of the prophecies and one of the stories that is very popular now, that's accepted now, is that it's very likely that King Kamehameha was born when Halley's Comet was visible in the sky above Hawaii. So that was about 17 something. I just looked it up, but I've forgotten the date now. And so in the late 1700s is when he was born and when Halley's Comet was visible from Hawaii. And that was one of those big signs, right? That this giant fireball in the sky is visible, and that is a Ilona or a sign that someone really important was going to be born. Another kind of fun story was that supposedly his mother craved the eye of a tiger shark as a food that she wanted to eat when she was pregnant with him. So in Hawaiian culture, we have a sometimes think of different characteristics of what a mother is craving is going to influence uh, what kind of baby she's having, which is very interesting as well. So that's just a couple of stories that I wanted to share with you today. And I hope that everyone here can enjoy or has enjoyed Kamehameha Day and is inspired to go and learn more about this public figure. So mahalo nui for having me, and I hope you enjoy also the rest of Shadow the Scientist tonight.
Mahalo nui loa, Leilani, for sharing your knowledge with us to broaden our horizons and understanding of this important day here on this beautiful island on which we are blessed to live. If you all have any questions for Leilani, more about King Kamehameha Day or Hawaiian culture in general, please feel free to drop those in the chat. Okay, so our guide has now joined us in the Zoom room here, Brian Lameau. Brian, how are you?
I'm well, thank you, Jamika, and thank you, Leilani, for sharing your incredible knowledge with us and the celebration of the day that we all had off until now.
Mahalo nui. Actually, I forgot one more thing. I
Yes, please.
promised at the beginning of my intro that I would mention an upcoming event that we have. So let me just share my screen again really quick. So this Saturday in Hilo, if anyone in this group or who watches this recording later happens to see this video before June 15th, in Hilo at Liliuokalani Park and Gardens, we're having an Ohana stargazing event. So this is a completely free event where we're going to have telescopes and just enjoy what is hopefully a nice starry summer sky in Hilo. But I'm really excited that we have two local cultural practitioners, Lelehua Ewan and Uncle Kimo James P. Hana, who are going to be sharing different sky stories with us that night. Um, So please come by if you have time and you're interested in hearing these stories. So June 15th, 6 to 9 p.m., Liliopolani Gardens. All right, I'm done now. Mahalo.
Mahalo, Leilani. Okay, so let's do some astronomy. So we are here at the Gemini North Base Facility. My name is Brian Lameau. I'm a research scientist here at Gemini North. I work on very, very distant galaxies for my research, and I spend a lot of time observing with telescopes, including the Gemini North telescope. I am not observing tonight, so I'm observing the observers, and I guess y'all are observing me. And so in the control room, which you can see, let's see, I'll spotlight it. Yeah, so I just spotlighted the control room camera for everybody. This is actually just down the hall. Also in the base facility, these are our two observers for the night. Charlie's on the right and engaged in, yeah, there he is. And Jenny, there's our operator for the night. So Charlie's in charge of most of the instruments tonight and kind of the science plan and where we're moving in the sky. And Jenny's moving the telescope, keeping an eye on the safety systems, making sure that the telescope and all the instruments are performing well. And if anything happens to go wrong, Jenny's the wonderful safety net for us to fix all the system, software, hardware, or anything that needs to be done. So we're actually at effectively sea level here. We're in Hilo on the Big Island, on the east coast of the Big Island. We're about 30 kilometers away from Maunakea, where these observations are being taken. They're at about 4,000 meters above sea level. So that's where the Gemini North telescope is. And so we're nice and comfortable here in the base facility. We have our coffee, we have our air conditioner, and we have, most importantly, our brain power, because when you go up to the summit of Maunakea, things get a little bit dicey in terms of your ability to think. There's 40% less oxygen. And so we're nice and easy here, and trying to use what neurons we can throughout the night to get the scientific observations that we want to get. So it is a beautiful night on Maunakea. I can share some cloud cameras. Let's see. Hello. Let me turn on this one. Okay, so hopefully everybody can see this now. These are cloud cameras from the Keck telescopes. So if everybody can see my cursor, the Gemini North telescope is right over here. This is on the east summit or east plateau of Maunakea. The twin Keck telescopes, which are just a tiny bit bigger than our telescope, are sitting here on the North Plateau along with the Japanese Subaru telescope. And then there's a smattering of other smaller telescopes and sub-millimeter telescopes for optical near infrared telescope, as well as Keck and Subaru. And so this is looking in each direction. These cloud cameras are very, very sensitive. So this is an upcam looking in between the two Keck telescopes. You can see the Keck telescopes are open tonight. You can see the cloud layer on top of Maunakea. So the inversion layer is good tonight, keeping the clouds down below the summit of Maunakea. This one I think is looking north. You can see the Gemini telescope here, and yay, we're open. So we've had a very tough winter here in Hawaii in spring. Lots of winds. In fact, I was observing last week 3 nights, and 2 of those nights snowed on the summit of Maunakea. So lots of humidity, fog, inclement weather. It's June in Hawaii. It's not supposed to snow, but it did. So obviously when it's snowing, that's not great for astronomical observations. So we have just an absolutely gorgeous night. And you can see the Milky Way starting to come out right now. Let's see. So the way that we observe on the Gemini North telescope is everybody in the world proposes for time on the telescope. We have 6 major partner countries but we have an open skies policy, so anybody in the world can apply. And we choose, I think, Jamaica, you said this in the introduction, we choose based on viability, so what's up in the sky at a given time, the conditions that are on a given night, so if there's lots of clouds versus if there's not so many clouds like tonight, or no clouds whatsoever, which is the way we like it. How turbulent the atmosphere is, or the ground layer, so near the telescope, how turbulent the air is, how bright the sky is, so if the moon is up as it is now versus when the moon is down and what phase the moon is in. We choose which observations are optimized for that time of year in this place for the conditions that are available for the night. So we have a person during the day that chooses those observations. We have a set of observations that we can choose some. So on a given 6-month period, we probably have, I don't know, 500, 1,000, 1,500 different observations that we could take. So that's a lot to choose from. And unlike other telescopes like the Keck telescope, Subaru telescope, where generally it's dedicated for a certain team on a given night. So scientists come, either they zoom in and use special software to control the telescope, but they have a certain scientific program and that's dedicated for that particular night. We choose a variety of different observations, and it can be anything that anybody proposed for, assuming the conditions are right for it. So we have a person during the day that chooses the suite of observations for a given set of conditions, and they have to make about somewhere between 10 and 13 different plans for the night. It's a super intense process. Usually they're spending from like 7 o'clock in the morning until 5 o'clock at night, just laboring over these different plans so that the observers can be prepared for the night to have out of these 1,000, 1,500 different observations, they can choose depends on how long the observations are, but somewhere between 5 and 20 different observations, unless it's a Alopeke night, in which case it's hundreds, that are optimal for a given night, for a given set of conditions. So Charlie's following that plan tonight. So we have determined what the conditions are tonight. They're wonderful. We have, maybe you'll hear me say it later, or you might hear Charlie or Jenny say it later. We have certain designations. We love acronyms here. So the designation for tonight in terms of the image quality, which is the turbulence of the atmosphere or the air near the telescope, we're in conditions known as IQ 20 or IQ 70, which means that we're in the either 20th percentile best or 70th percentile best conditions in terms of turbulence. So the air is not super turbulent tonight. We have no cloud cover, which is wonderful. The moon is not that bright this evening. So we're going to be mostly observing in the optical wave bands, which is basically what humans can see. If the moon were really, really bright, what we would look at is in the near infrared. So this would be redder than what humans can see because the moon is not so difficult in those wavelengths. And I don't know about water vapor, but we're not taking near infrared observations, so we don't care too much about how much water vapor is in the atmosphere. Not near, is it?
It's a little more. Can I join you on this camera?
Oh, of course you can. Yes, please do.
Let me see.
So let me remove the spotlight here.
Shall I open?
Sure. Yeah. Cool. So this is really informal. So please, for everybody who's joining us, feel free to ask questions in the chat. If you have a question that you'd like to ask verbally, please feel free to raise your hand. And Jamaica has a question already.
All right.
Please.
So you were first you were highlighting the control room, and we have Charlie and Jenny that we're going to be shadowing tonight. Now, in previous sessions, you've been in the chair where Charlie is. So can you tell us about these two roles?
Sure, absolutely. So I think Charlie's a bit busy at the moment, so Charlie, Do you have a second to
Yeah, sure.
introduce yourself and maybe talk a little bit about your role?
Sure. My name is Charlie Figuera. I'm one of the SOS staff here. I've been here for about just over 3 years now. I am serving as observer tonight, which means that I am going to be watching the weather conditions to choose from those different cues, those different possible plans of observation that Brian was mentioning. We have a number of different cues that are for different permutations of weather, some with more clouds, some with less, some with better seeing, better, more clarity of sky, some with worse, and lots of permutations thereof. And so I'll keep an eye on the weather, work between those different cues to pick out the best science that we can do for the conditions we have. If we have observations that are very, very demanding of really high quality weather, we don't want to do those when the weather is lousy. And if the weather is really good, we don't want to be doing observations that can tolerate much more lousy weather. So that's a lot of what I'm doing here over the course of the night. So I'm setting those up. I will direct Ginny where to slew, where to move the telescope to. She'll set up guiding. She can talk more about that, I guess. But then I'll run those observations and be looking at the data as it comes in and planning on what observations we do next. So it's it tends to be a very busy role over here. Tonight, it looks like the weather should be nice and stable, which means it'll be a little bit easier. Then we can just sit in one queue, one of those different variations, and run it out. So we don't have to make a lot of decisions about which queue to move between. But if conditions start getting a little more variable, that will have to happen.
Thanks, Charlie.
So that's about what I do.
Let's make it a boring night.
You know what? As long as we're open and taking data, I'm good.
Yep.
I'm happy with whichever.
Yep.
And we want you to be happy, Charlie. We want you to be happy. And we also want Jenny to be happy. Jenny!
Hi. I am the operator. We work in a 2-person team every night usually, and the operations side is something I'm very familiar with. I've been doing it more or less since 2004, various telescopes. And for one, I have a very distinct job of protecting the telescope from observers. And
It's only like Brian is observing.
and protecting.
And Zach too, come on.
Zach or Emma.
Especially Emma.
Oh yeah, go ahead, sorry. Okay. Protecting the telescope from weather, for example, and protecting the telescope from itself. So when problems happen and there's errors or software glitches or issues or mechanical problems, I will get notified somehow from our sensors, and I'll look into the problem and I'll try to fix it as fast as possible to get back on sky.
Jenny, let me interrupt you for a moment. Can we please slew to Q22 observation 3?
Sure. So while I'm slewing, I've been recording stable and guiding from the previous observation. I learned that we're using
Doing some imaging with GMOS.
with GMOS. We're going to use the OI guider, which is different from the guider we were just using. Set it up for that change. I'm now slewing. One of the first things I'm looking for, guide star even there, and if it is, I center it and set up guiding for it and make sure things are stable and that everything looks right. And when we're guiding and everything's stable, I hand things back to Charlie, and that's when he can start acquiring the target and taking data.
Sorry, Charlie, could you repeat the program designation? Was it Q222?
This is Q222, yeah. So we're doing some imaging of a celestial object, which shall remain nameless. We're doing some galaxy imaging. I'll say that.
And every time we slew, we're at a different elevation, different azimuth position, and the telescope pointing is going to be just a tiny bit off. So as I correct it, I can absorb those offsets throughout the night, and they will be stored and added to a sort of pointing model. More accurate with the start of each slew as time goes on.
Yeah, please.
We have a question from Eric. Do you also have individuals at the telescope site to work on issues, or is all of this hands-free?
So I'll take this one since I know Charlie and Jenny are busy getting it set up. Yeah, so we have a huge team here at Gemini North. We have software engineers, we have hardware engineers, we have summit crew that physically goes up to the summit. Every day they leave very early in the morning and they come back down at 4 p.m. So they're, doing the demanding job. They're going up, they're acclimating at 3,000 meters, and they're going the rest of the way up. It's a pretty tough job. It's physically intensive. And again, with 60% of, oxygen at sea level, it's a very, very demanding job. If something goes wrong during the day, we have instrument scientists like myself. So supposing something goes wrong with an instrument, I might be called, or I share instrument scientist duties with another person. And so that person may be called, or we're both called. And if we're at the base facility, because we travel a lot, we do things around the world. If we're at the base facility, we would probably come to the control room. We would talk with the summit. We would talk usually with our colleagues that are software engineers or hardware engineers. We have some knowledge of some of the subsystems of the telescope. I have a reasonable level of knowledge of the instrument that I help to support, or the main one that I help to support. I am on all the instrument teams here. But as far as like the subsystems, how the software interacts with the hardware, those I have less knowledge of. And so there are people that are very well versed in how connecting the various subsystems. And so I would rely on their expertise as they would rely on my expertise for understanding how the instrument works, the mechanics of the instrument, and then how light interacts with the instrument and how science gets done with the instrument. So I think we have something like between 50 and 80 people here at Gemini North, and Gemini has a twin telescope, or almost a twin telescope, in the south, in Cerro in Chile. And there's a lot of expertise down there as well. And so there's some expertise that we have that they don't have, and vice versa. And so there's scientists and engineers that travel down to the south, or they come up here to the north. We recently had somebody from the south doing vibration testing on our telescope. So looking at, we turned off one of our instruments. This causes a lot of vibrations on the telescope, which is the instrument I'm in charge of. So it's kind of a troublemaker. And the idea was to test what vibrations occur during like kind of normal operations without that instrument, to see if those were within thresholds for upcoming instrumentation. So when the instrument that I am in charge of either gets retired, or we take it off the telescope for a period of time to put another new developing instrument on, are we within thresholds to be able to use that instrument technically? And if not, what do we do about that? And so that person is at Gemini South, very well versed in the mechanics of this and how to make metrics and make tests that make sense and that can give us sensible results, so that we can say, yes, we need this. We need to be able to dampen such and such vibration, or no, this is not technically feasible. We have to go back to the instrumentation team and say,
starting science as soon as I.
You're okay. I muted you or muted him.
All right, starting science.
Okay. Yeah, so trying to be really cognizant of the observing team. The most important thing is the science is being done. We do all of this work so that the observing team at night can get the science done that everybody asks for. Telescope time is very precious, depending on where you're applying, anywhere from, let's say, 30% of teams that apply to 10% of teams that apply get time on the telescope. And of those, maybe 50% get the observations they want in a given semester, so a given 6 months. And so, it could be 5% of the people that apply actually get the time. And so we want to, whatever time we have, we want to utilize it to the absolute maximum. And that's what all the work during the day is for, to get to this moment now where we have great conditions, telescope is operating perfectly, instruments are operating perfectly, knock on wood. Charlie can say, let's go here, let's do this thing. And we can get exactly what the proposing team wants, the observations that they want, so that they can go back and then do the science that we're trying to facilitate. So hopefully that answers your question, Erich.
And all this happens while we're asleep. So we sleep, we wake up, and all the calibrations and repairs and maintenance that they've been working hard on all day.
Hopefully.
Yeah, we get a update, a sort of overall review of what has happened and what's available to us to so that, yeah, as we're operating, we can get right down to business and have everything be as efficient as possible.
Yeah, and vice versa. So, I mean, the night crew does an awesome job every night, like logging everything, all the, anything that happened during the night, even the smallest hiccup, that's logged. And so we have an operations meeting in the morning, which I'll be going to tomorrow morning. We review what happened the previous night. Charlie, as the observer, is in charge of taking the writing down a night log. So it's very detailed. It says we moved to here at this time. We took such and such observation, or we attempted this observation, a cloud came in and we had to pivot to another observation, or we attempted this observation and one of the instruments that we were using isn't working very well. So Jenny, did such and such and rebooted the system. And we lost 5 minutes, but we were able to get back onto the target. Or, it really seems like something's wrong. Day crew, can you please take a look at that? We're going to not use that instrument for tonight, and we're going to pivot, and we're going to make a whole new plan for tonight. And so that's the dreaded call that the person coordinating the queue does not want to get, which is that, hey, thanks for working all day and making these beautiful plans. Guess what? One of the instruments that you counted on for the vast majority of the observations for that night is not working, and so we need you to at midnight make a whole new set of plans for us. I've had to make that call, and I've heard that call on the other end. It's not a fun call in either direction.
Oh, I can only imagine. Okay, so yes.
I'll just tell one anecdote, which is that so this wasn't an instrument problem, but one night when I was observing, our fire alarm was triggered, and it wasn't because of a fire. We had a faulty sensor, and this had happened several times during the day, and I think at least one other time at nighttime. But somebody was able to drive up and turn it off. That night we were not able to drive up and turn it off, and it was a moonless night. And the strobe in our dome at the 5th level of our dome, so where the telescope is very bright. And so moonless night, bright strobe. And so we can't observe in the optical because there's a fire alarm going off, but we could observe in the infrared. But because we're sharing this MAUNA with not only cultural practitioners and a lot of other people that come up to commune with the cosmos, but other telescopes, they don't particularly like when you shoot a giant beam of light at their telescope and instruments. And so I called the Q coordinator that night, the person who was deciding what observations to take, and I said, hey, listen, so moonless night, we're usually observing in the optical. So all the observations that were planned were for the optical. Can you switch everything over to the near infrared? And so that we don't shine our strobe light at other observatories, can we look only in the eastern direction? So only for rising targets, because we're on the eastern plateau, as I showed earlier. And so if we point to the east, we don't flash the other observatories. And I heard a cry of abject pain that I had not heard from a Q coordinator before. And I said, okay, never mind, maybe let's cancel the night. So that night, unfortunately, we had to cancel. And the telescope was fine. There was no fire or nothing like that. Yeah, that's, that's the worst call you could possibly get at midnight.
Would anybody drive up to the summit at midnight just to put some duct tape on the?
Usually they save the emergency trips to the summit for factors that can that are dangerous, things that have to be taken care of, or else problems could cascade. So I am sure that at that point they said we're not gonna drive up, because it's basically about a 2-hour trip up to the summit, including a half-hour stop at 3,000 meters to acclimate to elevation. So,
And they still have to work a full day the next day.
and then so usually if there's a problem that is could cascade into more faults, more damage potentially, then they'll go up. But otherwise, they won't go up for the fire alarm.
Yeah, we thought about it, and it was midnight already. And so it was like, okay, if we go up, or we ask somebody to go up and then we come back down, by that time it's already, I don't know, 3 in the morning at best. And so it was, I don't think it was winter. So it was, probably we stopped observations at 4:30, 5 in the morning. And that was if we got like everything done immediately, like we knew exactly where to turn things off. And it was myself and an operator that was relatively new, so we don't necessarily know where the fire alarm button is or how to turn off a sensor. And so we could have had somebody, that was that trained in this, but then again, as Jenny said, we'd have to wake them up, and then they would have to work, the day shift. And so we just said, you know what, let's save some human capital here and not do that, because you don't want to make the day crew mad, because they're shepherding the telescope during the day and making sure everything's working well. So we had one other question from Jamin about adaptive optics system. So let me see if I can bring up. Charlie, do you have an ALTAIR ISD on one of your screens that I could shadow?
Let me pull one up in just a second. So if you look at, can you look at monitor 3?
Yes.
All right, let me. So I usually don't keep this up. This is usually an observer, an operator role to pay attention to DM screens, to device manager screens. But there's our ALTAIR ISD. So that's basically showing you the light path.
One second, let me share the screen.
Oh, yeah.
Okay, we got it up.
So you're showing the light path of ALTAIR right there. So I don't know if you can see, you can see my pointer. So essentially light's coming in our opening shutter, and it's going to be diverted to analyze over sort of on this side of the process. And then that light is going to be exit. It's basically it's being processed over here. That information is controlling a deformable mirror, which is correcting for atmospheric conditions. And that light will pass on through to the instrument at the bottom of the all of this is at the bottom of the telescope, but this will pass on, the light path will continue to our science instruments. Right now, we're not using ALTAIR. We only use it for certain observations. And our observations tonight do not require adaptive optics to reach the science goal.
Yeah, so we're in a relatively dark period in terms of the moon. And so, as I mentioned earlier, these are typically nights where we'll observe in the optical. So we have 3 optical instruments on tonight. One is GMOS. So that's Gemini Multi-Object Spectrograph. That's the one that Charlie, I think, is still observing on now. And this is actually an imager and a spectrograph. So we can either take just a straight up image in a certain color. And that's, I think, what Charlie's doing now. So we're looking in maybe the I band or the R band. And so this is like reddish light. Or we can disperse the light and create a rainbow and then analyze the rainbow. And we can do that for many objects. We can do that for a single object. It also has an integral field mode. So basically, it's a picture with a rainbow of colors at every location, so that you can get spectral information about the entire field of view, which is very powerful. So that's one of our optical instruments. Charlie's using that currently. The other one that's very commonly used on a night like tonight is called MAROON-X, and that's what's called an extreme radial velocity spectrograph. So basically very, very high resolution, meaning that you can separate out very, very similar colors from one another. So like red and just like a little bit redder than red. You can separate those out, and this allows you to measure Doppler shifts, so velocity changes of astronomical targets. It's usually used for nearby stars, to look for planets around stars, or to measure the chemistry of the atmospheres of planets that pass in front of stars. So if you have a star here, Gemini is over here on Earth, and you have a planet that passes in front, you can watch the spectrum, the rainbow change as the planet moves in front. You'll see absorption features, so certain types of light will be absorbed, and you could say, aha, based on lab experiments, you can say, aha, I recognize that particular wavelength as being an absorption feature of calcium. And so you say, oh, there's calcium in that planetary atmosphere, and there's going to be calcium absorption features in certain types of stars as well, but you're looking at the difference. So you get a spectrum of the star prior to the planet passing in front, then you get a spectrum with the superposition of the planet and the star, and you look at the difference between those two. So those are our two main optical instruments. And with optical light, currently anyways, the technology doesn't allow us to do adaptive optics. So adaptive optics, yeah, so that's maybe going to come in the future. There's plenty of people that are working on it. But right now, adaptive optics is only for what we call the near infrared, not even the mid infrared, but the near infrared. So this is from about 1,000 nanometers to about 2,500 nanometers roughly. So this is well read of what humans can see. And so you can see on this instrument status display that Charlie's sharing, this beam splitter right here. So this element right here, if y'all can see my cursor. And so this beam splitter, there's what's called a dichroic. I think it's marked by here. It's DIC. And dichroic, basically, a lot of instruments have them. There's probably if people have been to other sessions on Keck, maybe, I don't know if actually Raja uses LRES ever, but there's an instrument called LRES, which has a red side and a blue side. And so there's a dichroic, a beam splitter, and it basically shoots all the blue light to a set of dispersive elements, making the rainbow, and then shooting to a blue sensitive detector, and then all the red light to a red sensitive detector with a different dispersive element. And so this is the same type of thing, except it's taking all the optical light and it's measuring the deformations. So basically the difference between an ideal wave pattern and what is actually measured at the telescope. And then it's sending signals to this deformable mirror that Charlie mentioned to change the wave pattern around to be as close to ideal as possible. And so that you need some input for that. And so that input is the optical light. And then all the near infrared light is sent to the instrument. So you have this basically big bucket of light, and you say, okay, half of it I'm going to use as my calibration, and the other half I'm going to use to actually, measure the thing that I want to measure. And so that's all done in the near infrared. Currently, we only have one near infrared instrument on Gemini North, although another one is coming shortly. That instrument is called GNIRS, which is the Gemini Near InfraRed Spectrograph. It's also an imager. So we have a bunch of different modes. We have the imaging mode, so just taking pictures in different colors. We have the spectroscopic modes. So this is like just a slit spectroscopic mode, so single target or a couple of different targets, so objects in the sky, and you're dispersing the light, and you're getting a rainbow, but in the near infrared. And then we have two different integral field units. So we just added them as capabilities on the telescope. So I've been working for the last 2 years on getting that ready. And we finally got it ready. So we have one that's what we call a low resolution integral field unit, and that can be used with our adaptive optics system, but we use a mode called laser guide star plus P1. It's a weird term, but we have a peripheral wavefront sensor 1, where we look at a star somewhere kind of nearby the target, and we make wavefront corrections just in the same manner that I just mentioned to the wavefront coming from that star, and these are non-local. So this is a distance of I don't know how to say it, but up to about 5 arc minutes on the sky. So an arc minute is if you hold your hand out at arm's length, if you cover one eye, close one eye, a fingernail is about 1 degree on the sky. An arc minute is 1/60th of that. So 1/60th of a fingernail, so about 5/60ths of a fingernail, let's say 1/10 of a fingernail. So you can have a star that's about that far away from the object that you're looking at. You make a wavefront correction.
I'm going to stop you for a second.
Yep.
You said 5 arc seconds, correct?
Minutes, I think.
Okay.
Yeah, because P1, the probe arm, I think is like, is it 6 arc minutes, something like that?
And if you'd like to see, I was going to interrupt you. If you'd like to see some of our imaging data and you want to share screen 5, I can show you some imaging data that's rolling in right now.
Awesome, we'd love that. Let me put it up 1 sec. What are we looking at, Charlie?
All right, so this is the data that's coming in. All of our data is stored essentially as black and white data. If you take a look over here at we've got a little bit of information here. Down here we see filter 2 is set at I, which is an infrared band. So this is all light that's coming in that falls into that infrared band. And I don't remember off the top of my head what the boundaries of that band are, but we're looking at near infrared, just slightly longer than red. The color you see is false color. As I said, the image itself the data itself is essentially just black and white data, but we've got this color map that's showing us that's providing this false color. The imaging field, so this big box here represents the detector area for GMOS, and all of that detector area is used when we're doing spectroscopy. But when we're doing imaging, only this sort of central octagon is used. The detector is broken up into 3 segments. The yellow bands are the gaps in those between those detector segments. And you can already see a few things in here. They look fairly faint. I'll zoom in on some of them. But actually what I wanted to point out first is this long dark shape down in the corner. This is a shadow actually from our guider. The OI, or on-instrument guider, is a part of the GMOS instrument. And basically what it's doing is it's looking at a star right here in the field of view. It's essentially a specialized camera. And that's allowing us to compensate for very small motions of the telescope so that we stay pointed in exactly the same spot. Our telescope's motors, the drive system is very accurate, but it's not going to be able to compensate without some way of measuring exactly, much more precisely where it's at. So we usually take a guider to look at one of those stars. That's part of what Ginny sets up every time. But let me zoom in.
Charlie, if I'm not wrong, the guiding precision that we require is like less than 0.1 of an arc second, right?
That sounds about right. Yep.
Yeah. So if you take your fingernail again, so 1/60th is an arc minute, divide that again by 60, so 1/3600th of a fingernail, but you're not done yet, then divide by 10. So 1/36,000th of a fingernail. This is what we have to, this behemoth telescope has to be tracking to better than
Right.
that for us to do our science.
So, and the reason for that is without that, you know, these small, very small targets, if we don't have that precision, then over a long observation, and these observations, each one of these that we're doing right now is 5 minutes long. Over that observation, that star will wobble around. And so in 5 minutes time, it'll smear out. And this little pinpoint of a star will look like a big blob. So you lose that precision. I'm going to do a little bit of a trick here and just sort of adjust our scaling just a little bit. And all I've done is just essentially adjust the contrast levels. And now all of a sudden you can see a lot more in this image. And we see a lot of stars, but we also see a lot of blobby things, a lot of elongated things. Anything that's elongated that has some not circular, small pinpoint kind of shape is a galaxy. So you can see we are just littered with galaxies in this frame. I'll also note this one star right here that has this big red blotch. That is saturation. So this star is so bright that for this exposure, we're actually saturating. It's collecting more photons than the detector can deal with. And so they're spilling over and kind of making a mess of things there. That's not an issue, but you can see we've got a very faint blobby thing here. Looking at that, I would guess that we might be looking at some nearby dwarf galaxy, something like that, and probably some much more distant galaxies and all of these other objects. And of course, one other note I'll make, all of these very sharp, thin lines are cosmic rays. As they hit our detector, they make streaks. Those are removed in the data reduction process.
Yeah, so probably for this observation, you're going to be moving the telescope around a little bit, maybe taking 3 or 4 different observations, like kind of just a little bit around, so that you can average out all these defects like the OI occultation and cosmic rays and all this kind of stuff.
Exactly. And what that does, we do these little offsets between each observation, and that helps make sure that the cosmic rays are going to be random from one frame to the next. But if there's any variation in the detector surface, in the way that the detector surface is illuminated by the telescope, then those little slight offsets will allow us to correct for those, so we can get a much more reliable view. We just had another image roll in, and so the display here reset. This is our next frame. I really like this image that we're looking. Here's a very really edge-on galaxy that we're looking at, and you can see that thin edge-on shape, and even the core of the galaxy, the nucleus of the galaxy, right there at the center.
Charlie, do you think that's the target, or do you think it's the lower surface brightness thing?
I don't think that's a target. I think usually we do a good job of trying to come of more of. I noticed we're pointing at our first offset, which was essentially a 0-0 offset, and this was not at the center. So I don't think that's our target tonight.
Yeah, I would guess it's that like low surface brightness when you had the contrast set, the dynamic range is a little bit smaller.
Yeah,
you can see it pretty well. Yeah, so that guy that's moving around in the
this guy right down here.
Yeah, the lower left there, yeah, in that box.
That's my guess.
Yeah, so I think they're looking at local dwarf galaxies, so very low mass galaxies,
Mhm.
And they're trying to get distances to them and trying to understand how the dark matter profile interacts with the light there.
So we have a few questions. We have a hand raised, but before we get to Connor, Eric had a question in the chat. Because we're quite seismically active here, how do you compensate for that kind of activity?
Yeah, so there's a secondary effect of that. So before speaking about the primary effect for things actually moving around, this is something that I experienced on my last run, which was last week, last 3 nights last week, at the beginning of last week, so Monday through Wednesday of last week. Charlie, do you have a particle counter up by any chance on any of your screens? Otherwise, I might be able to bring up one here.
Yeah, count is screen 6.
Screen 6.
Our wavefront, our depth counter.
So do you have the particulate counter here? Or...
Oh, I'm sorry. I did not.
No, sorry. I was super impressed that you got it into your strip tools already.
No, we can't import that. We don't have that data imported yet. Okay, I'm sorry. I misunderstood what you were
No worries.
talking about. I do not have that loaded, and I really should.
The link for it? I can send it somewhere.
Yeah, I think I have it on this computer. Hold on, let's see if we can find it.
And I'm in Slack.
Is it the CFH one that you put in, Jenny?
I have a CFHT and I also have a Keck one.
Yeah, the Keck one's kind of hard to read.
Can we read those on internal until ops?
I think
They
we
come
have
up
them
on.
yeah.
CFHT one for
Yeah.
Let me stop sharing, and then yeah, they were really cool interface. Share. Okay, so here's what we were looking for. Oh man, these numbers are a lot better than when I saw them last.
Yeah, they look great right now, don't they?
Yeah. Oh my gosh. Okay, so but you can actually see the what I was looking at earlier. So this is a particulate counter from the Canada, France, Hawaii telescope. So this is just next door to the Gemini telescopes, just a little bit to the north. You can walk across and go into their dome if they'll let you. And yeah, so they have a particulate counter. We do as well. Keck telescopes do as well. Subaru does, but it's not totally calibrated yet. So I think they just got a new one. They're trying to calibrate it to Keck. So it's basically measuring airborne particles. And why this is important and why I bring it up in the context of the question is that Kilauea, which is one of the most active volcanoes on Earth, which is right nearby, just erupted for a second. It was about 3 hours, and it was a part of it that it hadn't erupted since like the 70s, I think.
Right.
Yeah, and so it was kind of a hiccup, and nobody was really like looking in that direction. And but what happened is there was a lot of off-gassing, and so there was SO2 and SO4 that was released, and it was released well after so it was released during the eruption, but it was off-gassing for a long time after the eruption as well. And so what we saw is particle levels. So back here that last week, so I think the eruption was somewhere around here. This is the last 7 days or so. Eruption was somewhere around here, maybe a couple days earlier. And we were like, oh, wow, that was a close call. Like, I mean, it's not that the lava envelops the island or anything. It's way off in the distance. It's not a threat to the telescopes or anything. But it was, fairly minor eruption by Kilauea standards. And so like, oh, okay, glad that's over. And then this is measuring, I think like particles per cubic centimeter or something like that. Every telescope has different units. We have, for whatever reason, we have like, initially we had like particles per feet squared, and then which doesn't even make any sense.
Yeah.
And then it became feet cubed, but it still doesn't mathematically make sense. So I think it's per centimeter cubed. And so we were observing, this was nighttime. I think the limit that CFH anyways has for their telescope is 20 on this graph. And so, we were kind of, okay, I think I was on this night, and we basically shut things down because there was a lot of humidity. And when you have humidity and SO2, That's not good because it can make acid rain, and that would be very, very bad. So we decided not to open, and I think just like the last 20 minutes, we were before it got too bright to observe. It was like kind of okay, and we'd already called the night at that point. And so I came back the next night. I was like, well, you know, that trended down, should be pretty good tonight. And then all of a sudden, whoop, it went right back up. And so there was plenty of off gassing still to be had, and you know, all that night we weren't able to open, even though the humidity wasn't that bad. It was like in the 50-60% range. We have to be really, really careful with the telescope when there's this much off gassing. And so then I finished my shift thinking, well, things are trending down. And then I said to the next observer, maybe you'll get to be open tonight. And whoop, nope, it went right back up. And so this is a big challenge. We had Mauna Loa, which is I think it's the biggest volcano in the world, that erupted let's see, about 17 months ago, 16 months ago, something like that. Yeah. It's right up here. So and that was crazy amount of SO2. And I remember I was on Subaru several of the nights, and you know, we could see the glow in the distance. It was crazy. There was tons of lava. And again, it's not threatening the telescopes on Mauna Kea, but just tons of off-gassing. And I think we were in the humidity range of like 40-50%, and the telescope operator there, because those kind of nights, I'm on the telescope for my own research. I really want to get the telescope open. You know, these are super precious nights. We wait for 6 months, we prepare everything. And the telescope operator said, I can't open the telescope because, you know, Mauna Loa is going off. And so that is an incredibly frustrating part about observing here. It doesn't happen that often, but it, you know, it can really mess up things, even though it's, you know, visibly there's not, you know, lava threatening the telescopes. The air quality definitely decreases. And, you know, we have very regular winds here in general. And so it generally takes that SO2 away from Mauna Kea. So with trade winds coming in from the northeast. But, you know, even just the residual detritus of that can be a problem on Mauna Kea.
Hey, Brian.
So, yeah.
Can you share screen? Can you go back and share my screen 6?
Sure.
Because there's another, I think the part of that question was actually looking at seismic activity rather than particulate. That's what threw me off. So I wanted to share something related to the seismic activity.
You're talking about strip tools?
Yeah, thank you.
Yep.
So this is a set of tools that we use to monitor a lot of, you know, a little bit of how the telescope is performing, but also how weather conditions. And the thing I want to point out is the plot on the upper right, which is, you know, a bunch of squiggles. And that's our tip tilt. So our guider is continually giving little updates along 2 different axes, tip and tilt. And those are just these corrections to the telescope so we can stay pointed, you know, very precisely. And they all generally look like this. When we do have earthquakes, you know, and earthquakes that we feel here. So, you know, we're talking high 3 moment magnitude or in the 4 moment magnitude. We can sometimes see that show up in the tip tilt. And so we'll see strong sudden shakes in that tip tilt trace. And so we can actually, you know, the telescope acts as a pretty sensitive seismometer in that way because it's trying to be very precise. For those small earthquakes, 3 and 4 magnitude, we typically don't have a lot of problem. And, you know, we'll get a fair number of those. Essentially the guider will correct for those shocks by keeping us pointed on target. If the shock is stronger than that, it will basically trigger alarms, and it'll stop the telescope motion, and the telescope will go into a safe mode. And typically then we need the day crew to go up, the summit crew to go up and verify no damage, to verify that everything is safe and sound. One of them, I've seen a number of those kind of things. Earlier this year, we had a particularly strong shock that was when I was on nights. It was, I think, around 4.6 or 4.7 moment magnitude, and we felt the shake in the control room. It was an earthquake that was down at whose epicenter was down at Kilauea. We felt the earthquake here. And then about 20 seconds later, we saw the tip tilt trace go wonky. And we could actually hear, we have speakers we have microphones in the dome. We could hear through the speakers the shaking of the dome. And it was really kind of fun because, I'm sort of an amateur geologist, as a hobby, and used to teach geology. And I sat down and I calculated, looked at the distance, looked at that time differential between when we felt it here and then the sound of the shaking and the tip tilt trace. And it worked out to pretty much exactly the speed of the S wave as it traveled through the Earth. So science works. Science. But yeah, generally seismic activity, most of the seismic activity we have here doesn't actually negatively impact our operations. Most of it, the vast majority of it is too small that even we don't notice. And even the larger stuff, a lot of times we can just keep observing right through. If it's big and if it's really big, then we'll have to shut down. We'll have to close up the telescope for the night and wait for the summit crew to get up there to check things out and to clear us.
Yeah, and that clearance is, there's a lot of checking that goes into that. So that would be all the dome, that would be all the telescope infrastructure, that would be all the instruments, making sure things didn't get dislodged. And
the hydrostatic bearings is a big thing. Make sure everything's sitting right, nothing got distorted.
Yeah, because if it gets distorted and shear forces, with all the weight that's on top, that can be very, very disastrous. So that's kind of like when if somebody falls over, you don't want to move them immediately. Like you want to stabilize things, make sure that you can move them in a way that is not destructive, that actually might help them. And so you want to make sure that you have that support if necessary. There's a lot of subsystems here that we got to keep track of. Charlie, are we still on the same observation? Are we about to pivot?
We are still in it. We are still on this one. It was a 50-minute sequence of 9 5-minute observations. If you do the math, of course, 9 5-minute observations doesn't add up to 50, but there's a little bit of overhead there in applying the offsets between each one. So it works out to about 50 minutes. We've got about 11, 12 minutes left on this one before we go to our next one. That's another one from the same program. So we are going to continue to do some imaging here with GMOS. But we'll get a different target in about 15 minutes or so.
Okay, so that'll probably take us through the session. Are you going to LP 110 afterwards, or is that not in the plan for tonight?
Oh, let me see. LP 110. No. Where do I even have LP 110 on my program? If conditions get to CC 70, we'll see LP 110. But right now we're in CC 50, and I don't expect that to change. So I think we'll probably not hit LP 110 tonight.
Okay, got it. Okay.
We're going to be sitting at this program till about 23:30, and then we'll move on to some other things.
Okay, so a bunch of different targets from this program. I guess this program is trying to build up a sample of low mass galaxies that are nearby. So sounds like you have like 3 or 4 targets for tonight. I think they had something like 20 targets, or at least they were looking to build up like something like 20 targets over the course of the semester or a couple semesters. So it sounds like we're going to make some pretty good headway tonight, hopefully.
Yeah, the conditions look real nice for it. We do have one IQ 20 target, so one really good seeing
Right, yeah.
environment target.
That's
and
like
we'll
that's like IQ 5, Charlie. They need delivered full width half max of less than 0.5 in the R band.
Yeah, that's
It's like
we
once in a
delivered.
lifetime.
If conditions are like they are right now, we should be in good shape. We're getting delivered at a moderate air mass here of around 0.45.
Yeah. So you for people online, you can see Charlie's written these tools. He's a bit modest and basically taken some tools that we already had in the observatory and made them look a lot better, a lot more functional, and a lot more helpful for observers at night. And so the middle left panel here is what Charlie's looking at for this measurement. This is to measure stars on the wavefront sensor. So we have this wavefront sensor that's guiding sensor, which Charlie was talking about earlier and Jenny was talking about earlier. And it's measuring the full width half max, so basically the spread of the light. So a star is big, but it's far away, so it's basically a point source, infinitesimally small as we see it. But the atmosphere and the ground layer turbulence blurs it out. And so this is why we get the twinkling of the stars. And so the less twinkling, less turbulence, the better it is for astronomical observations. And so our metric for determining the level of turbulence is this full width half max measurement. And so the green line is showing I guess it's reading out probably every, I don't know, 10 seconds, 20 seconds, something like that. A full width half max measurement, plotting it here. And so we're able to keep an eye on how blurry the stars look. And this IQ 20 line that's up at the top here, this is the 20th percentile best the level of turbulence that we get on Maunakea, and we're doing even better than that. So lower is better in this plot. And so this is pretty reasonable. So pretty good. You're lucky, like people that get observations under these conditions are very lucky. IQ 20 by default, by definition, it only happens about 1/5 of the time. So that's 20th percentile best. We have CC 50 tonight, so that's a cloud cover in the 50th best percentile, meaning basically no clouds. So half of the time on Maunakea, it's what we call photometric, meaning essentially nothing except for the atmosphere getting in the way. So IQ 20, so that happens 1/5 of the time. CC 50, that happens about 1/2 of the time. So IQ 20 CC 50 happens about 1/10 of the time. And so so that's already pretty rare, and we're doing better than IQ 20. This is probably like IQ 10 or something like that. And so as Charlie mentioned, we have this one like really technically challenging observation that if we get the conditions, and if we were taking it right now, we probably have it to be able to observe. So I can't remember what the program is, but it needs basically adaptive optics type seeing.
Wow.
But in natural seeing, so without the corrections in the optical. So yeah, going back to this thing that I was talking about a long time ago, this LGS plus P1 mode, this is basically what we call our super seeing mode on the telescope. It decreases the full width half max, the natural full width half max, by about a factor of 2. That's what this is akin to. We would basically need like LGS plus P1 level of seeing. So luckily Maunakea is helping us out a bunch tonight. So maybe we can get that, because I know that that program has been sitting around for a long time waiting for these crazy good conditions. So we've had a bad winter, bad spring, lots of things going on. And so law of averages, hopefully it's coming back on the other side of that. And looks like tonight's a pretty good indication that it is. And I think last night was absolutely gorgeous as well. I think it was IQ 20 pretty effectively all night, and no clouds.
Amazing.
So yeah, Charlie will be following this all night, making sure that things look okay. There's a bunch of different metrics on here which are important. There's other metrics which are on these big TV screens that are up above Charlie's head that measure other other conditions. And so Charlie will keep an eye on those, make sure that, you know, clouds aren't coming in, or if we were observing in the infrared, in the mid-infrared, or red part of the infrared, that there's, you know, the water vapor in the atmosphere is roughly constant, so on and so forth. So, yeah.
Could we see again kind of the images, the images of kind of the data that last came in?
Yeah. Charlie,
That's
remind me.
5.
5.
And we have several questions while we're looking at this awesome data. So Rob asked, how often does the ALTAIR give corrections?
The frequency is
Did that take that, Jenny?
Okay,
Yeah.
so yeah, that's a good question. So basically, depending on the brightness of the star, or it's mostly based on brightness.
Yeah.
But it could also be based on if we have cloud cover that's unpredictable and variable, and we think we might suddenly lose all of our counts, then we'll pick a higher value. But the ones that we have to choose from, let's see, on the P2, we have 200, what's it called? I can't even remember.
200 hertz. So
Right.
it's
Which is 0.005 second per hertz. So yeah, 200 hertz. We could do 100 hertz. We can do 50 hertz. Those are the most common ones for our P2 guider. And then for our OI guider, we have an additional option in the middle. What we're aiming for is 200 hertz because that'll give us the quickest corrections, more accurate guiding. But if we do have to go dimmer, the lowest we can go is 50 hertz. Or not dimmer, but slower, sorry.
So 200 times per second. And then ALTAIR, our adaptive optics system, if it's functioning well, bright enough star, no clouds, that's 1,000 times per second.
That's 1,000.
Yeah.
That's
I feel
unimaginable.
like I don't use that one very much.
Oh, we haven't been using it a lot now.
Yeah.
Okay, and we have
So
go
I was
ahead.
just going to say, so I've been measuring seeing on the image, picking out some nice, clearly stellar targets. You don't want to look at elongated targets for this to measure seeing, and our seeing is coming in around 0.46 arc seconds. So we've got some really nice seeing right now. If the conditions persist, we'll be able to get that high priority target tonight.
Yeah. And so going back to the guiding question, if I'm guessing it's guiding at 200 hertz right now, OI?
Yeah, we're actually at 50 hertz right now.
50 hertz. Okay. So we actually probably could do better then. So if we had a brighter star making
Sure.
correct 200 hertz, we might even be doing better than 0.45. Because
Yeah,
this is not measuring just
This is just, you just have a very faint, we didn't have any good bright guide star options. So this is the brightest we could get in the patrol field. So it's an interesting thing that the guide star brightness and our science brightness are, you know, two totally separate things. So we could have a bright target and a really faint guide star, unfortunately, or the converse. And that's, here we've got faint guide star and faint target.
And so the other option here, well, the other viable option would be the peripheral wavefront sensor 2, but I guess the field of view that would have called would be larger, plus there would be flexure, so it may induce some smearing to the light.
Yeah, P2 actually does not will not occult GMOS.
Ah, okay.
It's my understanding is that it's primarily a flexure issue. It's the preference is to use OI if possible. When we do non-sidereal objects, that is to say, things that are not do not move the way that stars do. So essentially anything in our own galaxy, in our own solar system, if we're looking at planets, if we're looking at comets or asteroids, those things move differently in the sky than stars do. And so OI cannot, the OI guider can't keep up with those. We need to use P2 because P2 can move faster and allow us to track those objects as they move across the sky. So that's typically where we're most using P2 in combination with GMOS. But otherwise, we try to use OI if we can, if we at all can. But as the observer, if I looked at the observation setup and we decided that we weren't going to be able to see the guide star, then I would switch to P2 and see if I could find something that we could guide on. P2 has a much larger and differently located patrol field, so a different selection of stars that it could see from. It basically forms a ring around the detector, as opposed to OI, whose patrol field is sort of a box shape, a box shape inside the detector. All right, Jenny, can we please slew to Q225 observation 25? Sorry, Q222 observation 25.
Sure.
So just to expand a little bit on what Charlie said, so here's a GMOS image. Sorry, an imager setup. So this is a scientific program which would use GMOS for imaging. And this is our observing tool. So this is what we use. Actually, Charlie's using it right now to set up the observations. We use the tool to put the observations in a place that the operator can see. And so they know where the target is. This is also where all the scientists, the proposing teams, set up their observations and work with us when we're working during the day as contact scientists to get the observations ready and optimized. And so here's the kind of a rotated view of what Charlie was just showing. This is the different charge coupled devices, so detectors on GMOS. Here's the yellow bands that Charlie was talking about earlier, the gaps in between the detectors. We have a blue, red optimized detector, and then a green optimized detector. That's what these BR and GR. These yellow circles, these are different dither points. So basically different movement points around the target, just like we showed earlier. So the targets move around a little bit, and this is to get rid of detector artifacts or the occultation from the on-instrument wavefront sensor. So here we have the drawing of the on-instrument wavefront sensor, and it's a probe arm that comes out. Here's the detector right here, this square thing, and it's selecting a star, in this case a fairly faint one. So the background image is a digital sky survey image, and so this is a fairly shallow image of basically the entire sky. And so we select stars based on their proximity to the target. So this box here is the mechanical reach of the probe arm. So basically a star can be anywhere in there, and I can, if I say, oh, I don't really like that star, it's not a good one, I can select a different star. So I can say, oh, let's choose that one instead. But that wouldn't be as good because it's closer to the target. So probably this is a smart choice. So you can see that the mechanical reach of the arm is basically on the detectors for the most part of it. About 3/4 of it is occulting the detectors, and then there's about a quarter or maybe a third that you can, if you get lucky, you can get a star there, and then you don't actually occult anything, and so then you don't have to worry about losing light in portions of the image. But a lot of times people are concerned only with the central portions of the image. But this is a great aspect of pretty much all astronomical observations. There's things that people are interested in, they propose for them. They say, I really want to know something about that galaxy, in this case, these dwarf galaxies that are nearby. But as Charlie showed, there's tons of serendipity. So there's all sorts of things that are in that field that probably, honestly, the scientists aren't going to analyze. And I've been at the telescope before where, for example, when I was doing my PhD in Davis, California, I went down to the Palomar telescope which is in the Grover Cleveland National Forest in Southern California. And I was doing observations for a survey that astronomical survey that I was helping to run as a graduate student. And we were looking for very distant galaxies that were parts of clusters of galaxies. So basically hundreds or thousands of galaxies all packed into one another, all interacting with one another and aggravating each other and so on and so forth. And so we were taking the kind of precursor imaging observations. So eventually we were going to do spectroscopic observations, but in order to do that, you need to take images in a bunch of different colors, so you can pre-select galaxies for follow-up with spectroscopy. So you take images of the sky, probably in a 5-minute image. At Palomar, it's a 5-meter telescope. We see certainly thousands of galaxies. This is with an instrument called the large format camera that was the prime focus of the Hale 5-meter telescope there. And so so we would take images in different colors, and then we'd say, oh, out of those, thousands of galaxies that are in that image, we're in particular interested in these 400. And so, then we would put slits on those. We would go to Keck, we go to a bigger telescope, we put slits on those, and then we collect more light. And then we try to figure out how far away they are and what their properties were. But the reason why I bring this up is that we went to one of our perspective fields to look for a distant galaxy cluster, took an image, and the first image, there was a giant NGC galaxy in the way. So it was a very nearby galaxy, super big. It occulted
Starting science.
Probably a fifth of the entire frame. And we could have still maybe done some science, the primary science. We still could have picked out some galaxies behind it, but it was going to be tough. It was going to be really, really tough to get anything.
This will be another 50 minutes.
And so we took probably 4 or 5 images. I called my advisor on the phone. I said, hey, listen, there's a giant galaxy in the way. Do we want to keep going with this? And we have other fields that we could look at. And we finally decided, no, let's move on to another field. But I actually used those images. Those were some of the deep, actually I think they were the deepest images ever taken of this NGC galaxy, because why are you pointing a 5-meter telescope at a galaxy that's nearby for 20 minutes or 30 minutes or whatever? That we were able, so I was able to take those images back and use it for a project for one of my classes, looking at the formation of stars in the halo of this galaxy. So in the very low surface brightness, diffuse regions of this galaxy, looking at basically the brightness fall off in different directions to see, to place constraints on how that galaxy formed. And so this is the serendipity that exists with any astronomical observation. And for Gemini, we do a great job of archiving all of our data, so it's publicly available. I think Jamika is going to put our Gemini archive link in the chat. And within 12 months, any observation is fully available to the public. And so you can go in, you can take a look, you can grab it out, you can do any analysis that you want. We have a bunch of data reduction tools so that you can make our raw data, in a form that's worthy of scientific analysis. And the Edge-on galaxy the beautiful one that Charlie showed earlier, you're interested in that galaxy, you could measure some stuff from that galaxy, and it's probably not that this proposing team would actually look at it. So coming back to the the wavefront sensor stuff that we were talking about earlier. So this is how this observation is set up. And this is a fairly faint star, so it's 50 hertz is the guiding rate. This isn't exactly the same observation that we were looking at, but one similar. And so, as Charlie said, let's suppose we didn't like that. As contact scientists during the day, we would actually probably set this up. So we'd say, yeah, you know what, we don't like that so much. Maybe you're not going to get what you want, especially for spectroscopy. You want to minimize the amount of gravitational flexure in between the wavefront sensor and the instrument that you're using. And so if you have an on-instrument wavefront sensor like this, it experiences the same gravity vector as the instrument itself. And so you don't have so much of a difference. With our primary wavefront sensor 2, it doesn't experience the same gravity vector as the instrument necessarily. And so there can be some differential movement because of that. So, but let's,
Peripheral.
sorry, what did I
Brian?
say?
Peripheral wavefront sensor.
Oh, did I say primary? Sorry, peripheral wave sensor. Yeah, thanks.
Gotta keep you honest.
Thank you, Charlie. So let's say we wanted our peripheral wavefront sensor too. So let's say we don't care about flexure too much and we just want a brighter star. So we want to guide it 200 hertz. So I could click on this one here and the star is much brighter. But this yellow region here shows the vignetting or occultation effectively of this this probe arm. And so the opaque region here, or nearly opaque region here, yellow region here, that's where the light is 100% vignetted. So if I were to say, I was able to put, sorry, if I really stupidly set up this observation, I would put the primary peripheral wavefront sensor 2 here, and it would occult this whole portion of the CCD. And so there we'd see absolutely nothing there. This more transparent yellow region here, this is partial vignetting, so you lose some of the light. And so this would not be good because the target would be partially vignetted. We would have to expose for a longer time. So vignetting is basically just taking away some of the light. We'd have to expose for a longer period of time in order to get the same number of photons effectively. So you'd want something that was really far out like this and is away from the primary target. And yeah, but that's not what we did for this one. This was OI, and that's probably the smart choice.
The software will keep you from doing stupid things with P2, most of the stupid things with P2.
Yeah, you can override it if you're feeling zealous.
You
Feeling confident.
You can't override it if you really. We will not stop you from doing stupid things.
Yeah,
as long as they don't damage anything.
Yeah.
Okay. I want to go back to a question that Raja, who of course is the Shadow the Scientist founder, put in the chat earlier. Could we go back to the graphs that you were showing us earlier? Raja's question pertains to those 6 or 8 graphs you were showing us.
Let me... Yep.
That's it.
There we
That's
are.
it. So Raja's question is: are the x-axis tick marks on the graph, graphs in units of minutes?
Yeah, they should be. Yeah.
Yep, they are in elapsed time. So the current data is at the far right at 0. That data is 0 minutes old, and then proceeding in age as you go to the left. There's actually a label on the bottom x-axis, elapsed time right there. So it'll show you the current time.
Oh, I see that. Okay. Okay.
Yeah. So we went away from these graphs for about 10 minutes, and conditions got a little bit worse, looks like. So now
Well, we are looking in we're looking in a slightly different location, a little bit lower elevation, a little higher air mass. So that's probably a chunk of it.
Charlie, which screen do you have the TSD on?
TSD's on 7.
Ooh.
Okay. So this is good context here. So this is like kind of lifeblood, just basic information about where the telescope's pointed and which instrument it's pointed, the light's pointed towards and everything. So this value right here is the value that Charlie was just referring to, is kind of a measure of the how much atmosphere that we're looking through. So it's called air mass, and it's the secant of the altitude. So air mass 1 means you're looking directly up, and air mass infinity means you're looking directly at the horizon. So this is where's the altitude number? Elevation. So we're at 53 degrees elevation right now. So we're pointed about halfway up or so. This is still pretty good for most astronomical observations. You probably want to keep it lower than 1.5 air masses. Optical is especially important because of refraction, differential refraction from the atmosphere. But yeah, this is so what were we looking at before, Charlie? Was it like 1.1 or something like that?
Sorry, say again?
Oh, the air mass of the previous observation.
Yeah, I believe it was.
Okay, so we were looking probably 70 degrees altitude or something like that. And so when you start to go through more atmosphere, for a given amount of turbulence, there's more spreading of the light, just because there's more material there. And so the seeing will generally get worse. That being said, the measurement, so the value that we're measuring with the on-instrument wavefront sensor is given here. This is the raw number that Charlie puts into his plots, is 0.32 arc seconds. This measurement, we generally add 0.1 or so.
About 0.25.
You had 0.25, really?
Oh, yeah.
For OI?
For all of the, for OI, P1 and P2.
Ah, okay. I was told it was you add about 0.2 for P2 and you add about 0.1 for OI.
No, it's about 0.25. Actually, it's I think it's actually about 0.28. I lied. Yeah,
Really?
so you're adding a lot more than that.
Oh, okay. Interesting.
And why do you add extra to that?
As far as I know, I would actually defer to Charlie on that one.
Oh.
Or
Yeah, so the we make an estimate of the guiding off the wavefront sensors. Those 3 wavefront sensors are not optimized for measuring seeing. They can make an estimate, but there are some systematic errors. So they are systematically all low just by nature of how the lenslets in that wavefront sensor are focusing the light. So if when we're using our adaptive optic systems, when we're using ALTAIR, it gives us a very precise measurement. But the 2x2 lenslets for the others cannot do as good of a job. So they're always measuring about 0.3 of an arc second small. So whatever they say, it's never that good. So if you were to flip back to monitor 6 to the charts, those charts actually, if you look at the legend here on that middle left-hand graph, you can see it says OIWFS, that's our onboard instrument wavefront sensor. The seeing measurement plus 0.28 arc seconds gives us a delivered value of 0.56. So that's really where we're sitting right now. And if you look at those 2 traces, the bright green one, the upper one is the delivered. So that's what you're actually seeing at the instrument. The dark green one below it is corrected for air mass. So this is what it looks like right now at air mass 1.25. If you were making that same observation at the zenith, you would be a little bit better off. Unfortunately, that doesn't mean if we go to the zenith, we'll see that, because we get variation across the sky. So, we're looking at a lower elevation to the north. The seeing there can be worse than it is at that same elevation to the east or west or somewhere else.
Charlie, that systematic offset for all the wavefront sensors, that's measured comparison between ALTAIR and OI measurements, or P2?
That's measured between, no, it's not measured to ALTAIR, it's measured to the to science data. So
okay.
we went over, we look at science.
Okay. So when you do the full width half max measurements in the actual data,
exactly,
systematically, you get a 0.28 arc second offset for OI and for P2.
Correct. So I'm going to go over here back to the data. which you can or may not look at. And I'm going to pull that up and start making, performing some of those measurements here. Picking some good sources that look pretty nice and round. There we're seeing some IQ 20. We're going to avoid measuring a source that's clearly elongated, that's an extended object. So we don't want to collect data. We don't want to measure seeing off of a galaxy. We want to measure seeing. And right now, as I'm looking at this, see, that looks like that's probably an extended object. I don't trust that. That one I trust. That looks like an extended object. It looks more blobby-like. That one does not look extended. So basically what I'll do is I'll measure a number of these across an image, and I'll pick stars in different parts of the image to get a good sample. Don't want to measure that one because that's a double of some sort. That one looks a little elongated. Here, this one right here. Let's see if, no, it's going to pick that. So I've measured here about 7 of these are scattered across the image. We're actually getting, we're still seeing IQ 20 here according to the data. So
every time you do that, Charlie.
in fact, if I go back up and I look at the plot that you probably just left, our trace has fallen back down again, and it agrees that we're probably sitting around 0.5, and we add that in. We always need to be very careful as operators, and particularly as observers, that we don't rely on this number very strongly. This is an estimate. Even that adding of nearly 0.3 of an arc second in is an estimate. Our best guess, what we really use this for, is to tell us that the seeing has risen up and then it's fallen back down again. We can generally rely on that, but in order to get a good understanding of the seeing, we have to look at the data.
And that's what ultimately the scientists are going to use to.
That's what the scientists are going to use.
So whatever other measurements we have, it's just a proxy. And
right. As the observer,
what's delivered.
As the observer, I can use that wavefront sensor trace there to get a feeling for it, but I never want to use that to decide what I'm going to do. I can look at that and say, I think we're probably in a good place that we might try to go look at that high priority, very low IQ observation here. If that trace was sitting up at 0.8 or 1, I would think, no, I'm not even going to bother. We're not going to be close to that. Here, I'm thinking we might be there. So we'll go there. We'll make a quick measurement. We'll see if the conditions are good enough to continue that observation. If they are, then we'll just run with it. And as long as the trace stays fairly constant, we'll be good.
So on your screen 5, the cycloplot display, what you were just doing is you were picking off what you determined to be point sources, so basically stars, or very distant shining black holes.
Correct. You're right. If it's a very distant shiny black hole, we'll count that as a point source.
Count that as a point source, yeah. And so you're picking maybe 5 or 6 or 7 across the field. Every time you pick one of these, it's measuring the light profile, so the radial profile as measly average of the light, and then it's doing a parametric fit, and then it's outputting the data that's on the values from that fit.
Right.
On the right-hand side there.
Yeah. So there you can see the fit. There's 2 traces here. It's fitting in X and Y. That's not what I meant to do. I meant to do this. There's our radial fit, which doesn't look very interesting because it's actually fitting a very large. Let me fix this a little bit. We'll do a little bit. 5 should be good. There we go. So there's a fit. You can see there's our profile fit, radial profile of that of this stellar object right there.
So I noticed actually, Charlie, that this program has X and Y binning of 2. So correct me if I'm wrong, but it's something like 0.08 arc seconds per unbin pixel, right? For GMOS North?
I believe so.
So it's 0.16 for when you bin by 2. So you make 1 pixel, 2 pixels, 1 pixel. That's what binning is. So
Right. So the algorithm here is so it's going to measure our full width half max in pixels, but it's going to take that binning into account for the final full width half max determination, the arc in arc seconds.
yeah. So I was just thinking the seeing is so good that they're almost under sampling the point spread function at this point.
Yeah, no, that's you can I keep doing the same thing. Almost. We still get a pretty good, I think we get a pretty good profile there that we can be fairly confident.
I just want to point out that the data that are showing, or the measurements that are showing at the just below that image, are not corresponding to this particular image, because it says image quality crap, and that's definitely not this image.
That is
Or is that something else that comes out?
That's weird. Why is that?
It did say like pixels, so maybe it was just picking up something else. Or sorry, it was saying 4 arc seconds.
So I think what happened is I went and changed the observation radius, or the measurement radius from 25 pixels down to 5, and it partially updated. So it made a mess of things. Yeah, I noticed that too.
That was great.
Yeah, don't even bother. Yeah. So I mean, basically the full width half max, it's like 2 pixels, 2 bin pixels almost,
Right.
2.5. Yeah. So it's just barely properly sampling the point spread function at this point. If conditions got any better, then we wouldn't even be utilizing these conditions to their full capabilities in this observation. But actually it can help because they're looking at a very low surface brightness galaxy. They're looking at like low mass, like low surface brightness galaxy. And so there, when you start binning really finely, in fact, when the conditions are really good, it actually kind of hurts you a little bit because it's just distributing that light over, much finer grid. So, so in some senses, it's maybe not the most optimal observation for the conditions. They don't require it anyways.
Yeah.
Oh wow. Yeah, but
I
mean, they'll still get great data. And actually they're probably looking at point sources. They're probably looking at variable stars. So I think they're trying to get distances to these galaxies. And so they're probably looking at variable stars. And so they look at the variations of the brightness and some of the stars. I'm taking a guess completely at this, but my guess is they're doing, you said they're doing like 6 5-minute images or something like that, Charlie? Or
9 5-minute images.
Okay, so yeah, they're probably just looking at variations within that over that time period in the brightness of some of the point sources. And then there's a relationship for certain types of stars. Probably Raja's the best person to speak about this, but certain types of stars, relationship between the period of the luminosity changes or the brightness changes, intrinsic brightness changes, and their intrinsic luminosity or intrinsic brightness. And so then if you understand how intrinsically bright these stars are, then you can get a distance to them because you know how apparently bright they are, and you know how light works, how it spreads out across the sphere. And I see Raja just came on to save the day. Hey, Raja.
What kind of variable stars are you talking about?
I'm not sure. My guess is they're Cepheids, but I didn't actually read the proposal, so not
Okay.
But it's nearby dwarf galaxies.
Got you. How nearby? Like a few megaparsecs?
4 and 8 megaparsecs looks like.
Okay. We have several. I don't know if this. So until a little while ago, we had a lot of students from the science internship program. Right now, we have Sunny from Molokai, we have Suela from Pristina and Kosovo, Lucky from which part of in the Bay Area, or am I getting that wrong? But we have a few students from our science internship program. It started this week, and some of us actually working on RLRE stars. Not Cepheids, but RLRE. And so we've been having this extended discussion about the physics of pulsating stars. And it's sort of ironic that pulsating stars are standard candles. Their brightness varies, yet they're standard. So we've been talking about that as well.
Madness.
Madness, yes. So what is standard is their time average brightness.
Oh, okay. I was going to ask. And there are various kinds of objects that are used as standard candles.
That's right. You know, many variable stars, not all, many variable stars make good standard candles. Cepheids, RLRE, supernovae again. It's, you know, their brightness changes, but it's their peak luminosity of type 1a supernovae that make them standard candles at peak brightness. Yeah.
Thank you, Raja.
Sure, I think.
So, Charlie, this image that you're showing has changed colors.
Yeah, so I readjusted the contrast to see some of the fainter objects here in the field of view. There are essentially 8 different amplifiers. So you'll see that there are these bands or 8 different amplifiers across the image that are, each band goes to a different amplifier, and each of those bands, each of those amplifiers has slightly different, essentially has slightly different levels that it's reading at. All of that will get corrected in the image reduction before it's ready for science use. But the raw data look, you know, we see this variation across the detector. The detector is not a perfect instrument. And so there's a lot of different corrections that need to be made in order to take that data and turn it into something science ready.
And so as we're looking at this image, and you all talked about that there's so many other things kind of in the background that the science team who put in this proposal, they're not even looking at that. So
They may not.
They may not. They may
choose
they
to.
may not. So once this data is no longer embargoed and it goes and it's searchable in the Gemini archive, how would you try to look at things that are in the field that was outside of the target image if you're looking at this in the archive?
So you probably do the same thing as you would do for the science team would do. They would take they would process the image using flat field images. So we take calibration frames. This could be depending if they need like an absolute reference point. I think this program actually looks at surface brightness fluctuations over maybe 3 or 4 patches of this very faint galaxy, diffuse galaxy that's at the bottom of Charlie's orange square here. So they use some method that I've never heard of before, which is it's just like aggregate surface brightness fluctuations across large swaths of the galaxy. And I guess apparently this is good enough to measure distances to like 15% accuracy. So anyway, so we would take maybe a photometric observation. Is this a program that requires a standard later tonight, Charlie?
We will be doing a photo standard at some point this evening. Yes, we'll probably do it actually after we've got one more from this program left. We'll probably go in take that float standard after this and then move on to that high priority target if the conditions still look good.
Okay. Yeah. So the basic idea is you take these calibrations, you take a star of known brightness, and you convert the number of counts on the detector or electrons on the detector into a physical unit. And so, of course, you're trying to take out all the properties of the instrument, all the properties of the telescope, the efficiency of the telescope, and all the mirrors that are inside, the efficiency of the detector, the atmosphere that you're looking through, if you're looking through any clouds, everything that is not the target itself, you're trying to distill the truth as much as possible. And so all these calibrations are aimed at removing the chaff and just getting the wheat. And so so any of the serendipitous observations, and in fact my first major scientific project was with Raja at UC Santa Cruz as an undergraduate, looking at serendipitous detections of very distant galaxies in a survey that was looking at distant galaxies, but not that distant. And so we would reduce the data in the same way. We would use the calibrations in the same way. And then we just had a slightly different methodology for, so we had things that were targeted, but then we had additional observations. So it was the multi-object spectrograph on GMOS on Keck. So GMOS is a very similar instrument when it's used in its MOS mode. So you just put a bunch of slits across the field of view. So you just imagine you pick out 30, in the case of DEMOS, you could pick out 150 objects of interest, and then you put a slit on them, and then that's all sent through a dispersive element and onto the array. You get a rainbow of colors for each one of them. But the slit is of certain finite length, and so you have your target object, and then you have a bunch of effectively empty real estate, or what you think is empty real estate. But every once in a while, another galaxy sneaks in. And so these were deep observations on a very big telescope, say that 10-meter primary mirror aperture for Keck, 8.1 meters for Gemini. So these are very sensitive telescopes and instruments. And so we were able to detect something like 20 or 50 distant galaxies during my undergraduate thesis, with Raja just searching through this archive and not even looking at the things that were the targets themselves. So there was, of course, tons of wonderful science that was done by people looking directly at the targets, but Raja had the forethought and the creativity to say, well, what about the stuff that's not those targets?
Yeah.
And then, hey, Brian, come here and spend hours looking at the data and sleeping on my office floor and all these things.
Time well spent.
Time well spent. Yeah.
Yes. Yes.
Best sleep I ever had after 28 hours of looking at galaxy spectra.
And speaking of Raja has another question, and this will be a great way to kind of wrap things up. Raja, go ahead. What's your next question?
I actually have a question about the detector we're looking at in front of us. You showed us the amplifiers, the different amplifiers. Is this 3 different CCDs?
Yeah, so there's 3 different CCDs here.
Each
in
with
the
4
detector.
amplifiers?
Yeah, so one across one in the left, one in the center, one in the right. Those bright yellow bands are essentially no data bands. That's the gap between those amplifiers.
Right. Because when you had a higher contrast, I could see these, I can still see them, these interesting circular artifacts along the edges of the CCD, almost like partial rings.
Yep, those are detector artifacts.
Something in the doping of the
I'll
silicon?
admit, I am not exactly sure what those are on GMOS. If I saw those in other places, I would think that there is that those are essentially dust rings, essentially. Here, I don't believe that's the case, simply because they are right along the edge. So I think there is a manufacturing defect along the side. Those artifacts are easily removed in the reduction process.
Of course, yeah, they look very subtle, but if you could zoom in, please, it's very
deep.
Sure. It's along all of, you see this, yeah, it's almost like bottle caps.
Yeah, but they don't line up across the gap.
Across the 2 sides, yeah, they're independent.
You can see they're very
Oh.
they're independent across the gap.
Yeah. And these are just minor variations in quantum efficiency. That's why I was thinking it's something to do with the
Yeah,
doping.
so, our counts right here, we're looking at counts on the order of, actually, I can tell you exactly. Over a little region right here, we're looking at median counts of around 10,708 pixels. If I take, or counts rather, if I take a portion of that ring, we're 10,749. So very small fractional variation, very small increase.
Yeah, it's the circularity of the pattern that made me notice that when you see them on all four edges,
Yeah, you do. I think it's there's an edge defect on the chip, I think is what we're
that's
looking
very
at. But I
neat.
don't know enough about the chip manufacturer to say that authoritatively.
Gotcha. Thank you.
Yeah, sure.
And this is actually the third generation of CCDs on GMOS North. And so this is these were just upgraded. That was actually a long time ago. Geez, it was like 2015 when this upgrade happened.
That sounds about right.
Yeah, and so I heard this mention that there was a manufacturer defect for these ones, but there's a lot less fringing than the previous
Gotcha.
CDs, and much more sensitive, especially the red-blue optimized CCDs is much more sensitive than red. So it can basically go up to 1 micron and down to 400 nanometers, 380 nanometers, something like that. So almost near the atmosphere cutoff, which is better than, like, for example, DMOS, but comparable to LRES. But yeah, I mean, I guess, Charlie, you have like what the dynamic range here from purple to yellow is like.
It's very high
Oh,
contrast.
it's about 600. It's about 600 counts variation from the purple to, from the darkest to the brightest in this image.
Yeah, I see that. 9191 to 9675, yeah. In the bottom bar, right? Yeah.
Actually, that's our low and high cut values over to the left side right over here.
Okay, well, I have to take a long trip tomorrow morning. So I think
Thank you for being with us.
I think we might call it here if that's okay.
Absolutely. Thank you so much, Jenny, Charlie, Brian, thank you so much for bringing us all together. Raja, of course, being the founder of Shadow the Scientist. This is an amazing initiative, and I'm so grateful to be a part of it. Really quickly, Brian, when can we expect another Gemini session?
Yeah, so the next session will be the next public session will be July 22nd. So yeah, I'm leaving on a trip tomorrow and going to the mainland and then to the other mainland in Europe. And so I'll be gone for 5 weeks. And so the day I get back, it will be July 21st, and I'll sleep a little bit. And then July 22nd, we have the next session. So this is the systems verification observations for a new spectrograph that we're almost done commissioning on Gemini North. So this will be our next facility instrument called IGRINS-2. We've talked about it in some previous Shadow the Scientist session. We had our instrument scientist on and our co-instrument scientist. And so we'll be taking the first mock real observation. So basically we have a bunch of scientists to propose for observations on this this new instrument. They say, hey, I think I can do this, and let's see. So the idea is, let's see. So can we do it? Can they get the science out? And does it work as advertised? And this will be, if everything goes well, this will be the only systems verification observation. So it'll be maybe 7 nights that we'll plan for it. And I think this will be the 5th of the 7th nights that we'll be doing the Shadow of the Scientist. And if everything looks good, then we release it for the public so anybody can apply. So that'll be super exciting. There'll be a lot of fanfare associated with it. This is the first instrument that the Korean Space Agency has built by themselves, and so this is a very big moment for them. They're one of the major partner countries for Gemini, and they, I think several of them the instrument builders and scientists associated with the building of the instrument will be here to hopefully celebrate a perfectly working instrument. So please stop by for that. I know there's a lot of Shadow the Scientist sessions in between then. And not only astronomy, yeah. And then I know that this fall, my research group, I think we have 6.5 nights on the Subaru telescope. So we'll be definitely doing a bunch of stuff with Subaru, and then probably Gemini South as well. So lots of fun astronomical observations coming up that y'all should shadow. And thank you very much, everybody, for coming along for the ride.
All right.
And nice to see you, Raja.
Yes.
Good to see you, Brian. Safe travels. I'm sorry I'll miss you in Hawaii.
Yeah, me too.
All right. Thank you so much, everyone. Have a good rest of your day, evening, or afternoon. Aloha.
Aloha.